We talked about yesterday is the fact that we can think of some things as being quadratic even though they're not truly quadratic. For example, if we take a look at, well, 1a, we have x to the 4 plus 9x squared plus 20. This is a polynomial, and in Math 30-1 we will learn that it is called a quartic polynomial. Quartic means the highest exponent or degree is 4. So it's not truly quadratic, but we can write it and think of it as being something that is quadratic. I want to do a comparison here between that and this. Probably shouldn't use p, it looks too much like a 9. I hope that everybody sees the analogy here, the comparison between those two expressions. Yes? Okay. What we would do is we would say this is quadratic. And what I would actually say, if I want to add more detail to that, is we say it's quadratic in R, which means R is the thing that's being squared in the first term, and R is the thing that's being raised to the 1 in the second term. And I didn't mention this yesterday, but we could say R is the thing that's being raised to the 0 in the last term. Okay? And we could even put x squared to the 0 over here by the 20, but that's not really my point. This is quadratic. Even though it's a quartic, it's a degree 4 polynomial, it's quadratic in x squared. It just means that we treat x squared in that expression like we would treat r in the other expression. And in this expression here on the right, if you wanted to factor this, you would put r and r here and here. You're putting in those two places the thing that the expression is quadratic in. And you would say, since 4 plus 5 gives me 9, and 4 times 5 gives me 20, that's the factored form of that expression. On the other hand, over here, you would still do the same thing, except you wouldn't put r here and here. You would put x squared here and here, because it's quadratic in x squared. So we treat the x squared like we would the r. And two numbers that multiply to give 20 and add to give 9 are 5 and 4. And again, I haven't really evaluated or had a chance to look at anybody's work yet on this. I get the feeling that this is going well. But just to make sure, ask yourself where this 9r comes from by looking at the factored form. It should be obvious with a little bit of thought that it's coming from the outer product, which will give you 5r, and the inner product, which will give you 4r. Ask yourself now where the 9x squared comes from based on looking at the factored form. And you should come to the conclusion that it's coming from the same place, right? It's just that it's not r's we're getting 4 of and 5 of. It's x squared. So we don't get 4r and 5r to get 9r. We get 4x squared and 5x squared to get 9x squared. And basically, for anything that looks like that, you can factor it that way. Now, all of these, well, no, there's one that isn't. I was going to say all of these are basically degree 4, but when you take a look at d, it's t to the 6 minus 4t cubed minus 21. This is quadratic in t cubed. And I'm just going to move that to another page. Didn't think that through very well. It's quadratic in t cubed because you can write this as t cubed squared minus 4 times t cubed to the 1 minus 21. I'm going to actually put in t cubed to the 0. Okay. What makes this quadratic are these three exponents. That's what makes it quadratic. Squared to the 1 to the 0. I realize going back here that when I wrote this x squared squared minus 9x squared plus 20, I didn't put to the 1 here. So the first term has to be some variable squared. In this case, it's x squared squared. The second term has to contain that same variable, x squared to the 1. The third term has no variables. Okay. This contains a variable, t cubed, to the 2 squared. It contains a variable in the middle term of t cubed to the 1, and there are no t cubes in the last term, so it's quadratic in t cubed. Even though it's a degree 6 polynomial, we can factor it like it's quadratic, which would mean, just to finish off my quick review here, this would factor into t cubed and t cubed, and I would be looking for two numbers that multiply to give negative 21 and add to give negative 4, and I get those. All right, take a look over your work, please. Does anybody have any questions you would like me to go over here? Go ahead, Ashira. 1S? F. Good. So you look at 1F, let me rewrite it here. It's 2x to the 5 minus 16x cubed plus 32x. And it's not quadratic in any way. We can't use this appearance of it in a quadratic presentation of it. And the main reason is this x to the 5 cannot be written as something squared because 5 is an odd number. If it were x to the 4, it could be x squared squared. If it were x to the 10, it could be x to the 5 squared. Okay. But we're not in an impasse here. We can do something because there are common factors in here. Each of these terms is divisible by 2. And each of these terms is divisible by x. Well, I'm going to factor the 2 out, okay? So the 2 is going to go away on the x to the 5. The 16 is going to become 8. The 32 is going to become 16. When you go way back to grade 10 math and you learned about factoring, I'm going to take a little bit of a detour here. And you're maybe asked to factor 3x to the 8, y to the 2, minus 12, x to the 6, y cubed. We can factor a 3 out of everything. Can we factor any x's out of that? How many should we factor out? And when I say how many, if you factor out x to the 4, we're factoring out x, 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 x. We're factoring out 4 of them. How many x's can we factor out? 6, good. How many y's should we factor out? 2. The point I'm making is the exponent on the variable that gets factored out is the smallest exponent in any of the variables. So 8 and 6, 6 is a smaller number for the x's. 2 and 3, 2 is a smaller number for the y's. By the way, just to finish this, you would have 1x squared minus 4y. Okay? But that's not the lesson. The lesson here, the little mini lesson, is you factor out the lowest exponent. So we also, when you look at this question that you've asked about in F, we also factor out x to the 1, which leaves us with x to the 4. If we had x to the 5 and we divide it by x to the 1, we're left with x to the 4. Minus, we took out a 2, so that's 8x squared plus we took out a 2, that's 16, and we took out an x, so the x is gone. And now what we have left inside is something that is presentable as a quadratic. Even though it's not quadratic, it's x to the 4, we can think of it as x squared squared minus 8 x squared to the 1 plus 16. So this factors further. X squared and x squared. It factors further because there are in fact two numbers that multiply to give 16 and add to give negative 8. Each of those are a difference of squares. So now we have 2x and then x plus 2, x minus 2, x plus 2, x minus 2. And you would probably write this as 2x, x plus 2 squared, x minus 2 squared. I mean, why not? Or rather than writing x plus 2, why don't we just say x plus 2 quantity squared? Other questions? Charlie?
Could we go over 10?
10? Certainly. It's a very difficult question, but we can do it. It's not so difficult that I would say, oh, we shouldn't even be talking about this. This is an academic math class. The reason it's difficult is twofold. One, let me just write this down first. Would you agree it's quadratic in x minus 2? Which means the first term contains x minus 2 squared, the second term contains x minus 2 to the 1, and the last term contains no x minus 2's. Okay, that's what one of the things that makes it difficult, is it's not quadratic in x. But the other thing is the coefficient of the first term is not 1, right? If that thing that I highlighted were 1, then we would put x minus 2 here and x minus 2 here. And then just look for the numbers. But it's not. And the difficult thing now is, and this is the worst part of this problem, is that is not even a whole number. It's a quarter. But we're going to kind of cheat a little bit here. Not cheat, but look at the answer to the question. Apparently this thing is equal to a binomial squared. That's what you're told. Which means that these two binomials have to be equal. So when we start saying, what do we put here and here, you know, you could, this is the first time we've ever factored something with fractions. You could put a quarter here and 1 there. But if these two things are the same, then this had better be 1/2 and 1/2. 1/2 times 1/2 will give you a quarter. If these two things are the same, then this had better be a 3 and a 3. I think this is an interesting question. Again, I think it's, I don't know that I would put this on an exam, but, and those of you that were in Sabre support this morning, there were a couple of you, we spent some time in Math 30-1 territory, and I ended the day this morning by telling them, you may not be expected to do most of these questions on exams, but after doing them, you're better, you're stronger, your muscles are more attuned mentally to doing the math. So there's value in working through this question. Do you agree, Charlie, that if I were to FOIL this out, the first would give me 1/4 times x minus 2 squared? Good. Do you agree that my last would give me the 9? Okay. What about my outer and inner? Well, my inner will be 3/2 times x minus 2. My outer will also be 3/2 times x minus 2. And what 3/2 is 1.5. If I have 1.5 pizzas plus 1.5 pizzas, I have 3 pizzas. So if I have 1.5 x minus 2's plus another 1.5 x minus 2's, then what I end up with is 3 of them. So, and we're not done, by the way. Okay? What we have to do now is simplify all of this, because we are asked for A and B. I think we're asked for the sum of them. So I need to simplify this 1/2 x minus 2 plus 3. I didn't quite say that properly. We need to simplify this 1/2 of x minus 2 and then add 3. So 1/2 times x is a half x. 1/2 times negative 2 is negative 1. So each of these is plus the 3. And here we're going to have 1/2 x minus 1 plus the 3. Each of these is 1/2 x plus 2. So rather than writing 1/2 x plus 2 times 1/2 x plus 2, we can write 1/2 x plus 2 quantity squared, and now it's ax plus b quantity squared. We can see that a is 1/2 and b is 2. Are we asked for the sum of a and b? Oops. So we're going to take 1/2 plus 2 and get 2.5. So can we just confirm, does the answer say 2.5? Okay, good. All right, we're going to, go ahead.
I was just wondering, could you multiply everything by 4 to get rid of the fraction?
No. And part of me was kind of hoping nobody would ask that, but I guess we need to talk about it. The question in front of us right now is this original expression. Can we just multiply everything by 4 to get rid of the fractions? And I'm saying no, and I'm asking everybody here, why not? By the way, do you see if you multiply everything by 4, you're going to have different numbers down here in your answer? You get a different result, which will be wrong. Why? Why are we not allowed to multiply everything by 4? Charlie, do you know?
Yeah, like the share
I couldn't hear who somebody was talking. Who?
Sorry.
Oh, it's okay. Don't apologize.
Because it's not equal to 0.
Right, it's not equal to 0. You know, if I tell you simplify this, okay, I say, what is that? I want it in simplified form. And you go, you know what, I'm just going to multiply everything by 4. I'm going to multiply the quarter by 4 and get 1. I'm going to multiply the 2 by 4 and get 8. So you go, haha, it's equal to 9. It's not equal to 9. 1/4 plus 2 is not 9. Since it's not equal to 0, you're not allowed to do that. Okay? And that's why when, Charlie, when you first asked about this question and I looked at it and I thought about it for a second, the very first thought was, okay, we need to clear the fractions, and then I realized it's not equal to 0, so we can't, which is why I said this is the first time we've been forced to factor with fractions. And it's a rare occasion where that's going to be necessary. Go ahead. 5a? Certainly. So we'll do 5a and then we're going to move on. So we want to factor this expression that's quadratic in 3x plus 1. And again, I don't mean to be overly repetitive, but I think it's important that you understand that terminology. It's because the first term contains 3x plus 1 to the 2, the second term contains 3x plus 1 to the 1, the last term contains 3x plus 1 to the 0. This is just like factoring that. Okay? And when you factor this on the right, you make a note, this is your eyeball, you notice by looking at the first term that the coefficient of the first term is not 1, and you can't factor that number out, so we're doing it by inspection. Okay? And are you okay with factoring by inspection, generally speaking? Like you don't use some other method. Okay. So, I mean, I suppose what I could do is I could factor this by inspection and then translate that to what I have over here, but I'm going to force us to just factor the original one. We have, I want to rewrite it, 4 times 3x plus 1 quantity squared minus 5 times 3x plus 1, and then plus 1. We would suspect, well, first of all, I mean, it must be 1 and 1. In fact, going even further, it has to be negative 1 and negative 1. Because we're getting a positive 1 for the product, but we have negative outer and inner terms because that middle term is negative. Our first suspicion, just like over here, our first suspicion over here would be to go 2r and 2r. So we would think it's 2 times the 3x plus 1 and 2 times the 3x plus 1. But if I do that, my outer and inner are each going to be negative 2 times 3x plus 1. And this is why we have erasers. When I combine these, I'm going to get negative 4 times 3x plus 1, and I want negative 5, so that's not right. I think most of us, or a lot of us at this point, would notice then that if instead of having a 2 and a 2, you had 4 and 1, it would work. Because now my inner is negative 1 times 3x plus 1. My outer is negative 4 times 3x plus 1, which gives me negative 5 times 3x plus 1. And now what we have to do, and this shouldn't be a surprise, this happens a lot of most of the time with these weird ones, we have to simplify this, right? So this is 12x plus 4 minus 1, and then 3x, well, 3x, isn't it? Because it's 3x plus 1 and then minus 1. So we end up with 12x plus 3 multiplied by 3x. I notice I can take a 3 out of that 12x plus 3. You always want to pause before you go, okay, I'm done, let's move on. Take a look at everything in the big picture and see if you can factor further. And finally, even though you're asked to factor, and 3 is a factor, and 3 is a factor, when we have numbers or monomials that are factors, we put them together as a single factor. And there we're done. Okay? Good. All right, we're going to move on here. This is the next lesson. So we spent 4 days on section 4.2. It was all about solving by factoring, and then also about factoring more complicated expressions by thinking of them as quadratic. What we're going to be looking at today and for the next couple of days of classes is solving. We're back to solving now. We're back to equal zero and finding solutions. We're not just factoring. In fact, we won't be factoring at all today. We're going to be looking over the next couple of days of classes at solving quadratic equations that have solutions, but we can't find them by factoring. Okay? And one of the methods you can use is completing the square. First of all, warm-up number 1, which is not going to require us to complete the square. Okay? But you do have to know how to solve these types of equations. If you look at A and you notice it's quadratic, we're back to normal, regular quadratic equations, not weird x to the 6th stuff. And say to yourself, I'm going to zero this equation. You're going to have to take this and subtract 37, and that will give you 2 equals 0, and that will give you 2x squared minus 32 equals 0. Are we okay with that? Can we factor this? Yes. We can take a 2 out. Can we factor it further? Sure, x squared minus 16 is a difference of squares. And now we're back in very familiar territory. I know we have to write this down, but x equals negative 4 and x equals positive 4. Right? There's nothing tricky about this. And I'm going to write down the complete solution. X will equal negative 4, or x will equal positive 4. Are we okay with warm-up A? Okay. So we don't require any new skills to solve the equation in warm-up A. Let's look now at warm-up B. Well, you look at it and you say, well, it's quadratic, so I'm going to zero both sides. I hope you recognize that zeroing the equation here, it would be wise to move all of the terms to the right side because you don't want negative quadratic terms. The quadratic term is negative 4t squared, so I'm going to move it over to the other side where I'm going to have 0 on the left. I'm going to have positive 4t squared. I'm going to have to subtract 11 and subtract 16. So I get 0 equals 4t squared minus 27. How's my math, my arithmetic? Good. So I'm not talking about now the difference that, one has 0 on the right and one has 0 on the left. But when you compare these two equations, they both started off as quadratic, missing a linear term. They just had a quadratic term and a number. We zeroed both of them. What is fundamentally different, and this is partly my fault, I have to remind you, I'm deaf, 100% deaf in one ear, and I have poor hearing in the other. Please don't just mumble out or say out an answer. Put up your hand. That's what I'm looking for here. Please and thank you. What's the fundamental difference now between those two equations? Yeah. Exactly. A we could factor, and in fact A was a type of question we've done before. B is not factorable. So how do we solve this? Well, we simply rearrange for t. I'm going to move the 27 to the other side and get 27 equals 4t squared. I can divide both sides by 4 and get 27 over 4. And now I can take the square root of both sides. When I take the square root of t squared, I guess I'll write square root t squared. I now have on the other side the square root of 27 over 4. What have I done wrong here? And it is wrong. It isn't just, it's a big deal. Yeah, Paige. Positive or negative, plus or minus. So I end up with t equals, and now I'm going back to, radicals are a weird thing because you kind of learn a little bit about radicals in grade 10, and we're going to learn more about them later this year, but you should know that I am allowed to take the square root of the numerator and the square root of the denominator. And the square root of 4 is 2. We're going to change that to 2. But the other thing, and in trig, this other thing cropped up from time to time, but it wasn't that big of a deal. We ended up saying in trig, it's not that big of a deal. Now we need to do it all the time. Is root 27 a simplifiable radical? And what you're doing there, I wouldn't call this scrap paper, I just want to do it in a different arena here so it doesn't clutter things up, is you're asking yourself, can I write root 27 as a product of two roots, one of which contains a perfect square? Is there a number that divides into 27 without remainder that's a perfect square? Well, 9 does, right? 9 times 3. And the square root of 9 is 3. So these are the same. And we say in math that 3 root 3, bless you, we say in math that 3 root 3 is simpler, simplified. So that means our two solutions are plus or minus 3 root 3 over 2. Could we have done the same thing with the equation in A? The equation in A was 2x squared minus 36 minus 32 equals 0. Am I right? Okay. Could we have said, well, I'm going to move the 32 to the other side. I'm going to divide both sides by 2. And then solve that equation for x? Definitely. So isolating the variable when there's no linear term, when you have x squareds and you have numbers, isolating the variable always works. Factoring only works if it's a difference of squares. But you're still going to get, when you take the square root here, x equals plus or minus root 16. So you get x equals plus or minus 4. All right. So this warm-up serves to illustrate that some quadratic equations are not factorable, so we solve them in other ways. Now let's take a look at warm-up 2. Solve this quadratic equation by factoring, and then just double-check the solutions. This is easy. Nope. We're back to writing equals 0 here. I hope everybody sees that it factors into x plus 6x minus 2. You all with me on that? I hope everybody sees that x equals negative 6 and x equals 2. Are you with me on that? Let's just do a quick check. If I were to put 2 here and here, you can check it in your calculator. 2 squared is 4. I'll just show my thinking here. 2 squared is 4. 4 plus 8 is 12. 12 minus 12 is 0. Jackpot, it works. If I were to put negative 6 in for x, I end up with 36 minus 24 minus 12 gives me 0. I don't want to spend class time graphing this. If you were to graph y equals this expression, the x-intercepts would be 2 and negative 6. All right? B, can this equation be solved by factoring? Are there solutions to the equation? And there's a typing mistake in your handout. Actually, you know what? No. Leave it alone. Does yours say If so, then what are their approximate values? Okay, that makes sense then. Are there solutions? If so, what are their values? So can it be solved by factoring? There's two ways that you can determine if it can be solved by factoring. One of them is to try to factor it and realize it can't be factored. The other one is to do the b squared minus 4ac thing. Can everybody do a b squared minus 4ac calculation for me? And these are calculations that should be fairly run-of-the-mill, this b squared minus 4ac. I want to say 56. When you square negative 4, you get, or when you square 4, you get 16. Minus 4 times 1 times negative 10 will be adding 40, so we get 56. So that's not a perfect square. The answer is it cannot be solved by factoring. That doesn't work. Are there solutions? Well, the only option we have here is to use our graphing calculator and see if the corresponding function has x-intercepts. If there are, then there are solutions. So we're going to look at y equals x squared minus, plus 4x minus 10. And we're going to look at the x-intercepts. Because we learned in the very first day of this unit that the x-intercepts of the corresponding function are the same as the solutions to the corresponding equation. Again, I know that a lot of us, maybe most of us, don't like doing this on the calculator, but we're going to learn something from this. We'll go zoom standard. Well, there are definite solutions. I'm going to adjust my window settings by trimming off a little bit of the stuff on the left and a lot of the stuff on the right, and going down to a lower y value of maybe negative 25. I mean, I'm just looking at the picture I had and adjusting where I want to look. That's pretty good. So what are these x-intercepts? Let's do the one on the left first. It's a 0. Put your cursor to the left of it, then put your cursor to the right of it, hit enter. One of our solutions is approximately negative 5.7 something. Repeat the process. The other one is approximately 1.74. So the x-intercepts are negative 5.74 approximately, and 1.74 approximately. These are the two solutions to the equation, approximate solutions. Well, this is an academic math course. We have to know how to find the exact values of those numbers, and that's what we're going to do now. If you cannot factor a quadratic expression to solve the equation by factoring, then you can still solve it by completing the square, and that's what we're going to look at. Solve this by completing the square. So, when we first learned how to complete the square, it was because we were trying to locate a vertex. That's not what we're doing here. There's no y. It's equal to 0. But we're going to do the same thing. We're going to say that I would like to add some magical number to these two terms. Don't forget about your minus 10. I would like to add some mystical, magical number that makes a perfect square trinomial. And you do that by taking the middle number, which is 4, dividing it by 2 to get 2, and squaring it, in this case, to get 4. And then I have to subtract 4 over here to keep things in balance. Don't forget now, this is equal to 0. This can be written as x plus 2 squared minus 14 equals 0. So now we're going to rearrange for x. And I want to highlight a few things that we have to get rid of. To get x by itself, we're going to have to get rid of this 2 at some point, aren't we? Somehow. To get x by itself, we're going to have to get rid of this squared somewhere along the way. And to get x by itself, we are also going to need to get rid of the minus 14. I mean, those are all things that are not x. We want x. What do we get rid of first? Nate?
Negative 14.
Right. Because it's the furthest away from x. It's like unwrapping something. You have to take the bow off before you can unwrap the box. And you have to unwrap the box before you can cut the tape to open the box. You have to work from the outside in when you're solving an equation. So I'm going to add 14 to both sides. And I don't know at this stage, do we need to write this? I'm not convinced we do. Not when we're just doing math. Maybe when you're doing an assignment, you might want to show that. That still leaves here, Nate, I'm going to stick with you. That still leaves the squared that we need to get rid of. Or if I can grab this. Yep, there it is. And the 2. Which are we going to get rid of now? The squared. And how are we going to do that? Square root it. So when I square root everything, I'm going to get x plus 2 equals root 14. I'll write this. X plus 2 squared, take the square root, equals root 14. How many of you would just write x plus 2 equals root 14? Okay. Would you actually write x plus 2 equals root 14, or would you write something different? Root 14? Just root 14? Plus or minus, right? So we'll go plus or minus here. My point about what I've written there is this right here, I don't think you need to write. I don't think you need to write that. If you simply wrote x plus 2 equals plus or minus root 14, that would be fine. Now we can finally get rid of the 2 by subtracting. When we do that, we almost always put the number that's not the radical before the radical. So this is my solution. What does that mean? X equals negative 2 plus the square root of 14, and x equals negative 2 minus the square root of 14. Please grab your calculator and figure out what the approximate values of those two numbers are. Do you recognize the numbers in decimal form? Well, you should. Those are the x-intercepts that we found. The negative 2 plus root 14 is going to give you the, I'm going by memory here, 5.74. And the negative 2 minus root 14,
No, it's
other way around. The negative 2 plus root 14 is going to give you 1.74. The negative 2 minus root 14 gives you the negative 5.74. It works. Okay, why shouldn't it? We didn't break any rules in math. So now we're going to practice this. Solve this equation by completing the square. So I'm going to rewrite this, leaving room to add a number. Just a piece of advice here. We have to write equals 0, but if I do this, I'm not going to have room to write that extra number to balance things off. So really space things out. What do? I add 9. Everybody give some thought as to why I'm adding 9. I'm going to take away 9. I'm adding 9 because half of negative 6 is negative 3, which squared gives me 9. So in completed square form, this is x minus 3 squared minus 36 equals 0. Get rid of the 36 first, then get rid of the squared, then get rid of the minus 3. X minus 3 quantity squared will equal 36. X minus 3 will equal plus or minus root 36. Hey, wait a minute. 36 is a perfect square. Okay, so we have x minus 3, we don't need brackets, equals plus or minus 6, which means x is equal to 3 plus or minus 6, because I add 3 to both sides. Which means x is equal to 3 plus 6, and x is equal to 3 minus 6, 9, and negative 3. I'm going to be, over the next few days of classes, trying to bring everything together, because everything we've been learning is connected ultimately. Can somebody tell me the significance of the fact that 36 is a perfect square? That we can take the square root of that number before we get x. You know? Right. If the solutions do not contain square roots, then they're rational numbers. And if the solutions are rational, it turns out you could have solved this by factoring. X equals 9, x equals negative 3. And I hope you would agree that if you had a choice, factoring is quicker. I think. All right, let's try another one. T squared plus 9t minus 7. Well, this is not factorable. So we're going to leave some room to add something. We have our minus 7. We're going to leave some room to correct something and then equal 0. I'm going to force us to work with fractions and exact values here. Half of 9 is 9 over 2. Squared gives me 81 over 4. I don't like writing fractions with a little slant angle, but because of that blank, I'm doing so. That means we have to subtract 81 over 4. Let's clean it up. T squared plus 9t plus 81 quarters minus, I don't care how you work this out. Use your calculator if you like. I believe it's 109 over 4 minus 109 over 4. But I would like a couple of you to confirm my suspicions. I'm starting to see some nods. Negative 109 over 4 equals 0. This becomes t plus half of 9, quantity squared, plus, well, equals, pardon me, equals 109 over 4. I moved it over at this point. I got to take the square root of both sides. T plus 9 over 2 equals plus or minus the square root of 109 quarters. Which means t is equal to negative 9 over 2 plus or minus the square root of 109 over 2. Because the square root of 4 is 2. Right? Root 109 quarters is root 109 over root 4. And we happen to have a common denominator. So let's put it all over 2. We're done here, but I really want you to understand what this means. When I say this, I will say t is equal to negative 9 plus or minus root 109 all over 2, which means negative 9 plus the square root of 109 all over 2, and negative 9 minus the square root of 109 all over 2. Couple more that we're going to do. The one that we're looking at now in question 3 is different. How is this one different than any of the completing the square ones we've done so far today? Yeah. The number beside the x squared isn't 1. The coefficient is what we call it, but that's okay. As long as you understand what we're talking about, that's better than not understanding at all. But we can say the coefficient of the quadratic term, the number in front of x squared, is not 1. So what we do is, you don't need to write this step. It's not necessary. But I just want to reinforce that the 2 over here is not really part of what's going on just yet. I need to factor the 3 out of both of these terms. Then I can worry about adding some number. What number do I add? I add the number 1 because half of the coefficient of x is negative 1. Quantity squared is positive 1. So what is wrong? What has a student done wrong if they say this now? Well, I added 1, I'm going to take away 1. What have they done wrong? Yeah.
We forgot to multiply it by the...
Right. By writing this plus 1 inside of the brackets, what I've really done is I've taken 3 and multiplied by 1. I've really added 3 inside of the brackets. So I've added 3 to the right-hand side of the equation. Well, I better take the 3 away. And of course, this is equal to 0. This becomes 3 times x minus 1 squared. 2 minus 3 is minus 1 equals 0. This time we have this to get rid of, this to get rid of, this to get rid of, and this to get rid of. Nate, are you up for it? What would we do first? Which negative 1? The pink one. We're going to add 1 to both sides. Good. And that's going to give us 3 times x minus 1 quantity squared equals 1. I'm not going to bring the colors down. Nate, what are we going to get rid of now? No. We can't get rid of the squared until we get rid of the 3. The only time you can get rid of the squared is if you have that thing squared equals something and nothing else. So we have to get rid of the 3 first, and we're going to do that by dividing both sides by 3. Now we can get rid of the squared. It will be x minus 1 equals plus or minus root 1/3 root 1/3 is 1 over root 3. I don't know if you remember this or not from the trig unit. Do you remember that 1 over root 2 is root 2 over 2? Well, this is root 3 over 3 if you want to go that route. I'm not going to worry about it. I'm going to come back to this in a second. Now I can add 1 to both sides. And this is where there's not a perfect meshing of all of the things we learn. And what I mean by that is there's some radical work that you haven't yet learned that could be useful here. If you were to look at the answer to this question in the back and you don't see this, but you see something else, use your calculator to find out if what their answer is equal to your answer. I'm not concerned today or in this lesson about simplifying these expressions. That will come later. I think you get the idea. I would much rather shave off one example and give you a few more minutes to practice here. The idea is that you complete the square so that the equation becomes a times x minus p squared plus q equals 0. And then you get rid of the q first. You get rid of the a next. You get rid of the squared third. And the last thing you do is you get rid of the p. Right, you're working from the outside in. You get rid of that q. Now it's gone. Now you can worry about getting towards the x by dividing by a, then taking the square root, then adding p. On Tuesday's class, you'll probably be getting your next hand-in assignment, but on Tuesday's class, we will learn a much nicer way to solve quadratic equations that are not factorable. And in the end, when you write your exam, if I give you a quadratic equation and I say solve it, you're going to try factoring, and if you can't factor, nobody's going to want to complete the square. Okay? There's a better option that we will learn about. Anyway, get started on that, and I will come around and give you a hand.